All right, in the last video, we talked about diagonal matrix, and we actually find a way of determining whether a matrix is diagonalizable or not. A matrix is diagonalizable if it has n linearly independent eigenvectors. In fact, it gave you a recipe for the change of basis matrix. You just put the eigenvectors on the diagonal, on the columns, and it gave us a recipe for the diagonal matrix. You just put the eigenvalues on the diagonal. So I want to try to apply this method to this matrix here. I want to diagonalize the following matrix. More precisely, I need to find an invertible matrix P and a diagonal matrix D so that D is P inverse AP. All right, so we know that P is going to be the eigenvectors as columns, and we know that D are going to be the eigenvalues on the diagonal. And so we need to start by finding the eigenvalues and finding a basis of eigenvectors. So let's start. What's PA of x? That's going to be minus 1 minus x, 7 minus 1, 0, 1 minus x. All right, so I'm going to expand on this second row. Everything else, yeah, everything else is gone. So I just have these right here. Now, sorry, there's a minus x missing. And now this is a nice 2 by 2. I'm going to get 1 minus x, minus 1 minus x, minus 2 minus x. Sorry, this one is not clear enough. And then the other ways is 0. All right, so it's already factored. I have minus x minus 1, x plus 1, x plus 2. And so I have 3 lambdas. I have 3 eigenvalues. I have 1, I have 1, I have minus 1, and I have 2, minus 2, sorry. So already from the last theorem, I know that I will have an eigenbasis for this matrix, and so I will have a diagonalize. It's a diagonalizable matrix, and so I'll be able to find P and D. All right, so we need to look for eigenvectors now. If I take a minus I, I'm going to get minus 2, 7, minus 1, 0, 0, 0, 0, 15, 2. So I know I'm going to have a free variable. I actually simplified it ahead of time. This is not one I'm doing in my head. Minus 1 over 5. Oh, sorry, this is minus 3. 0, 0, 0. And so I have one free variable. I have x, y, z, which is 1/5, 1/5, 1s. I'm going to take s equals 5 just to have nice s equals 5. I have a basis for E1 of A. That basis will be 1, 1, 5. All right, one down to go. All right, so if I put minus I get plus 1, so I get 0, 7 minus 1, 0, 2, 0, 0, 15 minus 1. So I have 0, 0, 0, and then the rest I have 1, 0, 0, 1 if I simplify. And so I have a free variable, which is x. Everything else is fixed to 0. So I have x, y, z is equal to 1, 0, 0, s. And so if I take s equals 1, I get my basis for minus 1 of a. which is 1, 0, 0. All right, finally, the third one is minus 2. Sorry, I keep wanting it to be 2. All right, so I get a plus 2i. That's going to give me 1, 7 minus 1, 0, 3, 0, and 0, 15, 0. Perfect. That will reduce to 1, 0, minus 1, 0, 1, 0, 0, 0, 0. And so x, y, z, let's see, I have one free variable. And so x, y, z will be x is s, y is 0, z is s. And so at s equals 1, I get b of e2 of a, e minus 2. Still such a bias for positive number. Get 1, 0, 0, 1. All right, so the P matrix, you just put the vectors that you found, and then the D matrix, you put their corresponding eigenvalues. So for the first one, it was 1 on the diagonal. Second one was minus 1. Last one is minus 2. And that's it. All right, let's recap how to do this. How to diagonalize an n by n matrix. First, you find the eigenvalues. For each eigenvalue, you find a basis for E lambda of A. If you get a total of n vectors, so in our case, we needed 3, we got 1 for each eigenvalue, we got 3, then A is diagonalizable. If you get less, then it is not. Then D will be equal to P inverse AP, where P has columns P1, P2, Pn, and these P1, P2, Pn are the eigenvalues, vectors, sorry, found in step 2. And then D are lambda 1, lambda 2, lambda n, and then a bunch of zeros, where lambda 1, lambda n are the eigenvalues of P1, Pn respectively. So lambda 1 is the eigenvalue of P1, lambda n is the eigenvalue of Pn.